Let's now consider sequential decision making. And this kind of idea that we're going to introduce now will come firstly under the umbrella term Markov decision process, or MDP. Now, we previously thought about reward processes. We had this one-arm bandit and we were pulling the handle, and the reward we assumed just depended on the action, and it didn't depend on the previous action or the previous state. It was just on the action. Often that's not the case, and it's a sequence of actions we need in order to get the reward, and we care about the sequence. An example of where this is the case would be, for example, finding our way out of a maze. We've got to get to the goal, so we're in one location, then we've got to move maybe along one bit to the left, bit to the left, bit to the right, bit to the left, and so on. And basically the state we're in at any particular time is determined by the action we just did before. So it's the sequence of actions we have to consider in order to get us all the way to the end, and only when we get to the end of the maze do we actually get any reward. Another case is driving a car. Imagine you're on a road and you're going to drive to the supermarket or something. You get in the car outside your house. Now, which direction you drive in? You're going along one road. It's the kind of the state you're in. You're in the car. The car's got speed. It's got this location on a particular road. Do you then turn left or right? Depends on the exact location you are in the real world. So you'll make a left action. You'll move along a bit further down the road, then you have to go right and what have you. And only when you get to the destination is your task achieved. I mean, that's kind of a reward. Another thing which very much depends on the sequence of the actions you make would be like a game of chess. Obviously there's another person playing as well, so they're making a sequence of actions, but what action you should take at any given time or any given state depends on what's happened in the past. So actually it's the state of the system that we're in at a particular time which will determine what we have to do next, right? So in particular, if we have a system such that future behaviour or what we have to do just depends on the current state we're in, then we say it's a Markov system. So if it depends just on the current state and not the whole history of states going up to that, then system is Markovian. So in other words, mathematically, we would say systems Markovian implies the probability of the next state given the current state is all we need to know, and we don't need to have the calculation what's the probability of the next state given all the past states. It's just the current state we care about. So we don't need to remember the state history. We can just use the current state in order to represent system. In fact, again, thinking about it in statistical terms, we say it was a sufficient statistic of the system is to know the current state. So therefore, the state S is therefore directly related to its successor state. And we often take advantage of this in reinforcement learning algorithms. So if you've got this property then, we've got this Markovian property and we can see all the states, it's fully observable, that's what we call it. We can think of that as a Markov decision process, or an MDP, and it's specified by then a set of states, a set of actions, a transfer function. So basically, given the state we're in, if we take an action, we'll move to another state, and what tells you how to do that is the transfer function. And there's also a reward function. So if we're in a given state and we take an action, the reward we get from that is given to us by the reward function. So let's think about transition function, and that's really a model of how the environment works in terms of the action, right? It indicates how we can move between states. So in this particular example here, represented by a graph, if we're in state 0 and we take, well, basically what we can do is we can take different actions, but in this particular example, the actions we're going to take are with 0.25 probability we go to state 2, with 0.25 probability we go to state 1, and 0.5 we go back to state 0. So the transition function would basically be which of these three actions we're taking from S0 and what does that relate to in terms of where we end up. So given the current state S, given the action A, the transition function gives us the probability we end up in a future state, right? Now we notice we can also have a deterministic transition function, but we can also think of that as being what future state do we end up in with probability 1, right? And we can represent these things as a table. This is, in this particular case, we're looking at the case where we have a stochastic transition function. So here we're saying if we're in state 0, right, and we take action 0, we end up in the following states with the following probabilities, right? We're in state 0, take action 0. With probability 0.07, we end up in state 0. With probability 0.9, we end up in state 1. Probability 0.03, we end up in state 2. And probability 0, we end up in state 3, and so on. So we can go down looking at the state, right? And we look at the action, and basically the transition function then gives, on the basis of the state we've got and the action we take, it'll tell us the probability that we end up in other states. And it can be, like I said, it can be deterministic. In fact, this particular line here, when the state is, we're in state 0, we take action 1, we transition to state 0. So in other words, we stay where we are in that particular case. In a simple maze example, we'd have, and you will typically come across this kind of maze example quite a lot. Here we've drawn some things on it to illustrate what kind of transitions are going to be allowed on this kind of system. We're going to have typically a starting state, which is in green here. We quite often will have a blocked state, so you're not allowed to go in there. That's not available. You're also not allowed to go off the maze, and probably there's a reward state or multiple reward states. Now, in these simple maze examples, what we're going to do is we can actually label the state on the state. So if you're in this cell, you're in state 1, in the next one, state 2 and 3, all the way up to the final one, which is state 12 up there. Now, in this particular maze, in fact, pretty much in most two-dimensional mazes, we limit ourselves to 4 actions, like going north, which is going up, going east, which is going east direction, going west. Sorry, that's west, that's east, and that's going south. Some particular explanations or derivations might also let you go diagonally, but we're not going to think about that. We're just going to have the 4, right? So east, west, north and south. Now the important thing is, if we actually go in a direction where we hit the wall, or we go in a direction that we go into a block state, what we're going to say is we stay put, right? Because if we're just, if I want to go from 5 and I want to go east, it's not allowed, so we end up staying there. So you can go through this maze and you can write down a transition function. This is a deterministic transition function, where we're actually saying, given the state we're in, let's think about the 4 actions and look at what state you end up in. So if we're in state 1, right, that's this state here, with state 1, and we go north, right, going north goes up, so we get into state 5, so we've got a 5 here. If we're in state 1, right, that's here, and we go east, we end up here, next one, state 2, and that's where this 2 comes from. If we're in state 1 and we go south, we try to go down, we can't, because if it bounces off the edge of the maze and we end up back where we were, so it's still a 1. And if we're in state 1 and we try to go west, we can't do that either, so we remain in state 1. So let's just look at another example now. Let's look at state 5. In state 5, right, that's here. If we go north, yes, we're allowed to do that. We end up in state 9, right? So that goes to a 9 there. If we try to go east, well, we're not allowed, are we? Because it's going off the maze, so you end up staying where you are. So we end up in 5. If I'm in state 5 and I go south, I end up here in state 1 again, right? So 5 south goes to state 1. And if I want to go west, I can't do that either because I've blocked it with this blocked state. So I end up staying put. and so on. You can go through the list and just check they all work. Now, a reinforcement agent, I've said this before, tries to maximize the cumulative reward that we're going to get. It wants to maximize the cumulative future reward, in fact. So what we're saying, at a time t, what we'd like is all the future rewards, basically, are going to be maximized. And we can add it up from the reward from the next step, from the next step to the next step plus 1 to the next step plus 2, next step plus 3, and so on. In fact, you can go all the way to infinity. And we can represent this by a sum. We don't have to represent it by writing everything down. We put it down from a sum between where we are to up to infinity into the future. Now, the trouble with that representation is sometimes we end up doing tasks where it doesn't ever get to the end. Now, if we've got that to be the case, then we're trying to sum up something to infinity, which is non-zero all the way through, and that means the sum will go to infinity. And generally speaking, what we do when we're considering these things is to use something called a discounted future reward. And this is represented by this gamma term. So the first reward that we get is just added up with a factor 1, and then we add it up with a factor gamma, where gamma is less than 1, multiplied by the next time step reward, and then the one after that is gamma squared, multiplied by the reward we get after that, and basically the gamma gets increased in power as we go along, and the consequence of this is, even if this thing never terminates, the fact that gamma n tends to 0 as n goes to infinity means we're okay in terms of having a finite future reward GT. Like I said, this gamma term's got to be between 0 and 1, and it also has advantages. It says we care more about things which can happen quickly than things that are going to take a very long time to actually happen. So another thing we can do is we can actually say, what is the value of a state? And if we can say the value of a state, we can look around one state to the states around it and decide whether or not actually they've got a higher value. So we should actually go into that state when we're looking for the action to take. So it basically, state value represents the value of a state when we're following a certain policy, and it will change on the policy because basically the policy is telling us what to do given the state, and it could be that if it's a random policy, you'll get a different result than let's say it's always trying to get you to go to the left or something. So basically then we can write down that the value of a certain policy for a given state is the expected expectation of the total reward on being in that state. That's what all it's saying. So basically, value indicates how good or how bad the state is. Right? It's a prediction of all the future reward in that state, and because of that, it tells us which way to go. So imagine we're on a putting green, or getting close to a putting green. In fact, we're not quite on the putting green. We're actually standing at the tee here. Imagine we could draw out lines, contour lines on the ground, and indicate kind of the value of being at any particular location with the ball at any particular time. What would constitute a great place to be? Well, obviously in the hole would be the best place. Being on the green would be pretty good as well, not quite as good. Bit further down, a bit further away, in fact all the way down to the tee, obviously the value's less and less and less and less. And really terrible would be if we managed to get into a bunker, especially if they're bunkers you can't ever get out of. So looking at this representation of value, we can see that what we'd like to do at any particular location, let's say we're in -2 in this region here, well, we'd certainly like to be in region -1, right? We'd rather be in -1 than -2 because it's a more valuable state, and the -1 is only one step away from being in 0, which is actually in this particular case it's got the largest value, it's got the least negative value in this case. So this is indicating then the gradient, if you like, of which way to go in terms of moving from one state to a better state tells you which action to take. In this case it would say move here to here to here to here to here to here to here. And we can do the same thing on a maze using a value function. If we say we want to get to the goal, and this is pretty much exactly the same as the putting green, actually, as an example. Let's say we want to get to the goal, but we're going to punish steps away from the goal by -1. So if we're only allowed to move, let's say, one step at a time. So at the goal, we're out. You know, we've solved the problem. So what will we do? Well, we can take actions north, east, south, and west as usual. And the state is the particular number of the cell that we're going to be in. So, but what would the rewards look like? Well, let's say we just put the intermediate reward. So that's basically what we've just said is the punishment, right? So we're saying reward is -1 per time step, right? So in other words, if we're in one state and go to another, go to another, go to another, it's always a -1 immediate reward, right? We're always losing. Wherever we are, whenever we make a move, we're losing -1. And that's what this is indicating. You know, we're in a particular state. When we move to, let's say, from this state to the one next door here, we get an immediate reward of -1. Okay. Now what we can also do is, on the basis of this, we can calculate what the overall value is, right? So let's look at how we get this. We're just going to do it in a simple by hand version, but this is something that we're going to use with our algorithm. But you can imagine if you're in this state here next to the goal, right? This state is obviously -1 because if you move from this state to the goal, you're at the goal and you didn't get penalised. But if you're in this state here, the one just a little bit to the left, and you move to this state next to the goal, then overall, from this state here to the one before the goal, is actually got a value of -2, right? Because it's going to cost you -2 to get to the goal from there. And the one a bit further up, well, that's another step away. So that's going to cost you what you get when you move into that, and into that. That's going to cost you then -3. And this will be -4, -5, -6, -7, -8, -9, -10, -11. Notice also then that's -12 there, but so's this one, right? So this is also -12, and so on, -13, -14, well, there's a few more things on this one than there are on that one. But you get the idea. So basically, when we calculate this state value, what we find is we end up with the values of the state as the cumulative reward to get to the goal, and we can then look at this, right? And if I was in any particular state now, like say I'm in -10 up here, in this particular state here, with a value of -10, I should say. Well, obviously, if we want to choose an action which moves us to a higher valued state, then it's going to move us in the right direction to get to the goal. We're going to go from -10 to -9. From -9, we're not going to go backwards because we can see that this state here has got a larger value, or a less negative value, and so on 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 and so on, like that. And in fact, that's exactly what you can do. You can then calculate the greedy policy if you know what the values are, because you can look at this and you can say, well, you know, like this one to here, you'd move along there, you go down here, you go down here, you go down here and off here. In this case, you'd go down here, along, up, across, up, and so on. So we can easily look at these and calculate what will be the greedy policy, the policy that gives you the best reward for a given state. And then we can then indicate it, as we have in this particular case, by pointing out which direction we should be moving in using an arrow in this particular instance.